from Ivoclar. I cover North Texas, Oklahoma, Kansas, part of Louisiana, so on the road all the time. And today we have our senior technical consultant with us from the headquarters that I invited him to come down and be with us and talk about a couple of new products that we have and the technology behind it. Bill Barton, he's 40-year dental technician and 25-year in the service. And he's been with Ivoclar for 13 years. So he contributes a lot to all the issues that you are having, contributes not to the issues, but he contributes to the solutions of the issues that you have. So 9 times out of 10, it's Bill who's resolving the problems. And he also contributes to the R&D department at Ivoclar. And so we're glad to have him. And please welcome Bill.
Thanks, Ely. I'm a little guy, so I'm going to come down here where I can hide. You know, my Michigan friends over here came all the way down with me to get some warm weather. Appreciate it. Yeah, nice seeing you guys. Hey, I'm glad to be here. Seriously, this is a fun part of my job. Many of you may know me. You may have talked to me on the phone or seen me speak before. So I kind of go all over the place. So my presentations are typically like if you're trying to drink water out of a fire hydrant. You know how overwhelming that can be because there's so much information. As laboratory technicians, we value that information, but sometimes it comes too fast. So if you have any questions, I say something that's not making quite right amount of sense, just kind of wave at me. We got a couple hours to go through 2 presentations. I'm going to try to do my best to do that, but don't feel that you can't interrupt me, because obviously if I say something or something is showing up here, it's not quite clicking or just went past, I want to go back, because you're not the only one that has the question. So don't hesitate to ask. I'll try not to get too deep into the weeds on things, because I'm down here in Texas and I'm not looking out my back door. That was yesterday morning. I'm like Mother Nature, April Fools, right? I was just starting to see some grass coming up in the backyard. These guys, they're a little bit ahead of me on the spring weather where they're at. I'm a little further north up in Traverse City, and I get lake effect all the time. So if you don't know what lake effect snow looks like on April 1st, that's what it looks like at about 8 o'clock in the morning. All right, so let's get started. So the overview of the Ivotion system, I'm just going to talk. Do I need to kill this mic? You got that one? Okay, getting a little feedback. Could be me just moving around. So I'm going to cover the Ivotion system just so you get an understanding of what that is. And then looking at the Ivotion disc itself, that monolithic disc, and where that plays, how it was made, and what it looks like. The physical properties and the scientific information, I'm going to touch bits and pieces of that, and again, not get too deep into the weeds. And then the updated use and indications. Current tooth molds I'll look at, tell you what's there, tell you what's coming. Expanded tooth shades, base shades, what's available there. A little bit of a 3-shape update for those of you that have been using 3-shape over the last year. You're going to have an idea what's in there. And then, of course, the geometry tips and tricks. I talk about the geometry. I do got to get up here so I can stay in tune with my slides. The geometry is that blue line, that ribbon that's within there. How many have used the Ivotion workflow? Any of you? Well, I know Mike has over here. So I'll get into the weeds with that just a little bit. And then finish up with manufacturing, because I can't talk about the Ivotion disc without talking about the mill system. So when we look at the Ivotion system in itself, we've got, let me back up here. Starting over here, I'm going to go left to right. The Ivotion is that monolithic disc, but don't get confused, because we have Ivotion Dent and Ivotion Dent Multi and Ivotion Base. So those are all Ivotion as well. The whole family is Ivotion. It's kind of like Emacs. Emacs is a family of materials. So that's what we have here. So I'll talk about Ivotion monolithic, and that's that dual material disc. The tooth libraries that are available in there right now, the Phonaris tooth is our main aesthetic tooth. So how many of you use the Phonaris? Traditionally, a few of you do. So that's our sexy tooth. This one is nice. It's got a lot of characterization. It's a nanohybrid composite tooth. So it just made sense when we were putting this library together that we built it initially with this tooth line. The next step coming in was the Vivadent SPE and DCL molds. Anybody using these teeth? These are a nice tooth too. You know where these teeth came from? The blue line. So if you've used the blue line tooth and you're very familiar with this A24B, in the blue line, you're going to have that same basic shape of that blue line tooth, but again, we made it sexy like the Phonaris tooth. We gave it a little bit broader neck so it's easier to set when you're setting these in a conventional denture. A little bit longer neck as well, and some surface characterization. So we made it a really nice tooth. So a big improvement over the blue line. Now the Ivotion library. The Ivotion library for the monolithic workflow, we started with that Phonaris 2 library, and we morphed it and adapted it to fit this geometry. So if you're getting your clinicians to prescribe the monolithic denture, you want them to use the Phonaris mold guide for that mold selection. Or if you're like 8 out of 10 labs are picking the molds anyways for the dentures, you're going to pick a Phonaris mold. It'll be very familiar with you. Now, if you're in the workflow of the Ivotion monolithic and you get to a point where it doesn't fit in the disc, or it's too tall, too fat, or just the geometry's not right, and so now you want to move to a carded tooth. Maybe you want to take that denture tooth off the card and put it in the socket and bond it. You can't do that starting with the Ivotion library and go to the Phonaris tooth, because we had morphed that Phonaris tooth to help fill out the geometry. And you'll see where that makes sense when I go forward. You'd have to go back and change the actual workflow. So the Ivotion system, and this is, Ely and Trish, whichever one of those two is your rep, they're going to talk to you about the options for the library packages in 3-shape. I always recommend when you call me and you ask, what you're looking for your libraries, I always try to steer you towards the bundle with the Phonaris 2, the Vivadent S, and the monolithic Ivotion. Even if you're not in our mill system and you're not going to be able to do the Ivotion monolithic, but you know a guy, that has one, or a gal who has a mill that maybe you want to outsource that to, or to an outsourced center, you can, if you have the library, you can design it, send it to somebody else, they can produce it, send it back, and you finish it. So starting off with the bundle is the best bet for your money. The rest of the libraries are sold individually. You can buy just the Phonaris if that's all you want to use. The blue line is kept out of the bundle. So the reason the blue line is kept out is, like I said, with the Vivadent S molds, we've actually made the blue line look better in that tooth mold. So it's not all the blue line molds are in there. The P molds are not. It's just the A molds and the most sold globally, not just in North America, but the largest selection of those come from there. So the blue line is an optional library to buy. Not many people use it. There are still some old timers that are stuck on the blue line until they see the Vivadent S, and then you got your favorite 2 or 3 molds you like to use. You'll find those in the S molds. It's just a much better tooth. So that's what the library looks like with the Phonaris 2. So you have everything in there in a small, medium, and large, soft to bold, or masculine to feminine. With the ortho tip, the 22 degree, and the lingualized occlusion schemes. And the nice thing with being digital in this milled tooth library you can change that. You can, if you need a 33 degree, you can just grab and morph a cusp and ridge and make it that for that specific scenario. Same if you needed a 0 degree, you take the lingualized, which I don't know why you would anymore, but and drop the cusp down to give yourself a flat occlusal table. The lingualized is my go-to. Glad to see you could make it, Chris. Had to do that. Chris is a good friend. Over at the VA, he worked for me in Germany, so I like to see old friends. Nice to see you. On the clinical side, the clinical instrumentation, when you were talking about digital dentures, this UTS CAD, that UTS CAD is a glorified Fox plane. That's going to give you some values on the bipupillary and the Camper's plane. So the ala tragus line is where we measure the Camper's plane. And we do that because, instead of the Frankfurt, because we use the Stratus articulator. Our Stratus articulator is based on that plane. And so we just bring it right into the software to be similar to that. When that UTS value comes in and you look at it, and it doesn't quite look like a right angle or a good restorative angle for you, you can go ahead and tweak that up or down to make room for the teeth. You know, it's the bipupillary is the one that you want to hold true to, because you don't want that denture going in the patient's mouth and being a little cattywampus. But the UTS CAD, it's not a mandatory piece of the workflow, it's just a nice clinical tool to get you the information you need to make this denture more successful. The Nathometer CAD, that's that device right there. Nathometer CAD is the Gothic arch tracing. There's probably 2% of the clinicians want Gothic arch tracing. You know, there may be others who are tied into it, but there's very few of those being sold. When I talk to the marketing manager on that, there's very few of those being sold. Most of them are universities. So maybe we'll see some fresh graduates come out of the universities and they're going to ask for Gothic arch tracing devices. That's what this is. It's going to capture your centric relation, and it's going to give you a much better restorative position for that denture. How many are familiar with the Centric Tray? Any guys using Centric Tray? The Centric Tray is our way of getting a glorified mush bite. This gets you the initial starting point. This is a big triple tray impression with a lot of putty. Goes in, the clinician guides the patient into what they feel is going to be a pretty good starting point for the restorative position. And now that's where you make your aesthetic control base from, or your base plate and occlusion rim. And that gives you a starting point, because they're going to take that base plate and occlusion rim and they're going to modify that, and if they're using the Nathometer, they're going to get that Gothic arch tracing, and that's going to come back to your final restorative space. So it's just one piece in the step that's going to get you closer. But all optional devices to make a digital denture, really all you need is impressions and a bite, and that's going to get you a starting point. These just narrow down some of the inaccuracies in denture making. So we look at the materials we have available today. And again, we pick on most popular shades. We know in North America and Canada, Preference is our number one shade in both IvoCap and IvoBase. That's our competitor to the Lucitone material. Pink V is a close runner-up to that. It's a little more opaque. You know, if you've used Preference, you know it's got a little translucency to it. And then our USD. Now the USD we've now modified, so this is our Ethnic Mahari shade. And the disc I have here is the one I just evaluated. And it's a little darker and a little bit of more brown to it, and when I like it a lot. So they've listened to us. We got some feedback from North America, and the manufacturing team, I think, hit the mark on this one. So the new USD shade we'll see probably on the market in June. The tooth shades in this disc, of course, we started off with the A1, the B1, the A2, and then we've slowly added in. The latest is the Bleach 3, the A3, and the A3-5 have all been included over this last year. I get a few calls for like a D2 or a C3, And we know those shades are being made, and so the more I hear from you guys on what you want, then I can poke the people in Liechtenstein and tell them this is what we need. The manufacturing of it of this disc is done in an industrial Ivo-based unit. It starts off as Ivocap material. The tooth material I'll talk about in a little bit is also PMMA, but it's all done under pressure and constantly injected, so you get a very dense material, just like you do with the Ivocap or Ivo-based system. So more to come on shades in the future. Probably it will be either late this year or next year. We'll add another 1 or 2 in there, both base and tooth side. So let's look at the disc itself and where this came from. As many of you know and have seen either some of the videos and PowerPoints I've done or my presentations elsewhere, I was on the ground floor with this starting about 8.5 years ago, working with this process. And this disc in itself, that was just the general digital denture. This disc itself came out of our second meeting in Liechtenstein. We were going through tooth libraries and our arrangements, and we sat down, Dr. Ronnie Watzek, prosthodontist in our R&D clinic, Dr. Frank Lasello, our senior prosthodontist here in Buffalo, myself, and Don Yancey, and many of you know Don Yancey, but we were sitting down in the cafeteria area, drinking a cappuccino on a break, and we started throwing out, how can we mill this all in one? Because if you think about it, back then, the big push for digital denture was kind of printed. Everybody wanted to go printed. They're talking printed. And so that was part of our conversation that day is, you know, can we go printing? Well, they poo-poo on the printing. So we said, well, how could we mill it? So Ronnie pulled a napkin out and started drawing. And we go, yeah, if you did this and you did that. So the rough concept began over an espresso and cappuccino and an ice cream bar on a break, and then it evolved from there. But we wanted something that was going to compete with printing because we saw that emerging, and we knew that we were not going to have a printed material in time to compete with a printed material, only because we will not come out with a denture-based material or tooth material that does not meet the ISO standard. And right now, all the printed materials that are out there don't qualify under ISO as far as a denture-based material when they're testing, because the ISO standard is based around polymethyl methacrylates and not the photopolymers. So there's more to come on that. So we wanted to make sure, I'm not saying good or bad or ugly about the printed materials, it's just as a company, we're not going to go out there until we have something as good or better than PMMA. That's kind of our stand on that, and our scientists are working on it. But we needed something that was going to compete. It was going to be something that was economical. You could still do individual tooth arrangements. The other one that was here was the Baltic Denture. That was, you know, you've seen the Baltic Denture. The initial ones were just 3. It was a small, medium, and large. And so we needed something that was going to compete in that basic arena at an economy type denture. But we still wanted it to be functional, to be able to move teeth, customize it for that patient, be able to morph the teeth, have good aesthetics. Doesn't necessarily have to be stellar aesthetics, but it's got to meet that good, better, best. It's got to meet that good denture. And then the elimination of the bonding process, because that's kind of the dirty part. Now we're back into working with free monomer and everything and mixing the chemicals. And if we can get rid of that step, one, we've made it leaner in as far as that manufacturing process goes, but we've gotten rid of the chemical out of the lab as well. And then to hit 90% of the patients. And we know this because in our other milled tooth workflow, or even the tooth carded workflow, not every patient can be done milled, digitally milled. You can design just about anything digitally, but you may have to go to a printer or then come back into a conventional processing workflow, because there are some cases that just won't fit in a 98 by 35 millimeter disc. So we know there's some limitation there, but we feel pretty confident you get about 90% of the cases. So that shell geometry I talked about that came up out of the conversation, when I got back to Amherst, or Buffalo, New York, it was about 3 months and this showed up for me to look at. And Ronnie and Philip, my counterpart in Liechtenstein, basically made these by hand in wax and then poured molds and everything. They showed me the concept. And we went through this and they came over and we talked about it even more. And again, we were looking at small, medium, and large, trying to fit this in. And of course, with curve of Spee, curve of Wilson, you know, everything associated with that, how do we get this geometry to work? And so they went through and along with the engineers and the guys with the big head that can do a lot of math, figured it out. We actually took 100 current patients they had in Liechtenstein, came in, scanned all their dentures. And then they took that and put it into a software, and that drove where the averages were. And so we were able now to design the shell geometry around that. So there's 2 discs. There's an upper and a lower disc, obviously, because the geometry between the two are slightly different, as well as the tooth positions and morphology. And you'll see in the geometry, when you bring in the library, the second molar is going to be much shorter than the rest of the teeth. We also had to lengthen those Fenaris teeth in order to help fit the geometry. So you go from the narrow arch, so you're on the curve and the narrow arch, and then if you go out wider, then you need that longer tooth to come down and capture that gingival section. And of course, dropping a tooth, typically when I'm doing a conventional denture or even a milled tooth denture, and I hit that 22-degree angle coming up the ramus, we don't set a tooth on that. You don't put a tooth on the ramp because that forces the denture, it dislodges it. So you drop a tooth. 9 times out of 10 in a conventional or a milled tooth workflow, it's going to be a bicuspid. And that'll give me enough room to put that second molar in, because I want the occlusal table for chewing versus the aesthetic at that point. That's the compromise. And you know, and just so I don't get that denture kicking out. You can't do that with this geometry, because if you were to take out a premolar and the molar moves into the next premolar position, your geometry and your gingiva is wrong. So you can drop a second molar in this case. That would be the sacrifice. And again, we're back at that good denture. And that's kind of what it would look like in the disc. So we're taking the 3Shape software with that blue ribbon, and that blue ribbon is identical representation in that disc. So the disc itself, the material, I talked a little bit about high impact optimized. People go, Bill, what the hell is high impact optimized? I can tell you this is SR Ivocap material, high impact in the beginning. But because this disc is 98 by 35, it takes a little while to polymerize. So those of you that have worked with Ivocap in the past, you know to drive off residual monomer, you leave it in the Ivo 4 bath for another 10 minutes. It cures the first round, 35 minutes, and to drive off some monomer in another 10 minutes. But once you start going beyond that, you start to really cause damage. The longer PMMA stays at that high temperature, the chemical properties begin to change, and now you start losing that high impact property. So the fracture toughness starts to diminish, the material becomes brittle. And so we know that this big disc, polymerizing it and trying to get it all done in 35 minutes isn't going to happen. So the sacrifice is we lose, there's 2 standards for high impact material that it has to meet to be called one. This slightly falls below one of those bars. So it's just enough that we can't say it's high impact, but it's pretty damn close to high impact. There's not much difference, but that's the fine line we walk to get these polymerized. And the other difference is the tooth material is also a PMMA material, which also has a little different curing characteristic than the base material. So we're balancing the two to get the nice homogeneous disc that is going to be strong and durable. High impact property, I just digressed a little on that. When you've got a monolithic denture, is the high impact so important anymore? With a carded denture tooth and in a conventionally processed base, high impact's pretty important. But when you've got a monolithic denture where the tooth arch is either bonded into place, I'll show some slides here in a second, is either bonded into place or it's processed in place, there's a lot of strength to that mass. And so the typical denture base at 2.5 millimeters is very, very strong. Well, the material, by the way, let me back up because I skipped over that real quick. For the tooth, I did mention PMMA. It is not a double cross-link. So again, if we were looking at a good, better, best, I'm going, okay, good, I'm putting in a highly cross-linked PMMA tooth. Better, I'm moving into a double cross-link. And best, I'm doing a nanohybrid composite Phenaris tooth. So this, again, falls into a good denture. And again, it is falling into the, let's say, economy line denture. And so this material, if you're familiar with our Ivostar and Athostar or the Vivadent PE, which we had discontinued, that old tooth line, this is that material. So still very tried and true material. The wear simulation of the teeth, because people kind of get wrapped up on how long these are going to last and what indications and how they perform. So this study was done. We did an internal study. There was external study, and it both in lab and patient. And the in vivo study will compare it. So on the left slide, what you see is the wear of the one tooth material. So basically, we'll call it the tooth. And on the right is the combination of the wear of the antagonist and the tooth. So when they're both rubbing together, some studies measure only one, the tooth it's on, and then some measure the space on both. But what we see is a consistency in a pattern. You know, of course, you're going to have a wider gap when two materials are being worn when you measure that space in between versus what was lost on the one. But you can see it's a very similar pattern occurring. So we feel pretty confident the measuring is correct. What you look at Phenaris here, and being a nanohybrid composite tooth and having that composite shell on it should be very resistant to wear. You now look at Ivotion next to it and Ivotion Dent. You know, they're all kind of fall in the same category, but the DCL, that blue line tooth over here, and then the TrueBite IPN sitting over here, you know, with a lot more wear in both instances here. We're trying to figure out and scratch our head, why are we seeing this? Because DCL's a harder tooth. You know, why is it wearing? And why is the Ivotion milled tooth and the Ivotion monolithic tooth not wearing as much? And we dug a little deeper and compared it to the intraoral study, and it showed a consistency with wear, what's happening in the mouth, what's happening in the lab. The red line shows a pretty straight, consistent measurement going on. They had actually a little more wear when it got in the mouth. When you're in front of a wear machine in the lab, and it just sits there and does 10,000 cycles of wear going in a little circle, you know, that's just that one movement. But when you get into the dynamic of the mouth and things in the position of the teeth and in where things are happening, they get a little bit more wear. But it was interesting. It stayed consistent with what we were seeing in the lab studies. And so around 600 was when you include the standard deviation, was about where we wanted to be with the tooth material. So what we found was that the wear simulation of the teeth correlates with the clinical wear, like I talked about. The DCL1 and DCL2, we have now 3 generations of DCL material, you know, they wore more than the Phenaris did, which was obvious. The wear simulation method for the tooth, what we found was the differentiation in the materials. So how that denture tooth is made. That carded denture tooth is made in layers and processed. They do the enamel layer, then they do another layer, and then another layer. Some are 2, some are 3, and some are 4-layered teeth. And as these are being processed, there's some, again, back to the heating of this. These are all heat-cured materials. There's some material or physical properties being diminished each time it's polymerized. So that is where the wear is coming in. So a little bit difference in the material where the discs are polymerized one time. So there's no layering and multi-polymerization steps involved. That's why we see that the PMA tooth is wearing very comparable to the Phenaris tooth. So fracture resistance. This little study we put together in Amherst, and we took the Ivo base with individual carded teeth injected, the Ivotion monolithic, and then we did the Lucitone print with their IPN CAD. And this was a couple years ago we started this. And what we do is we make this jig and we load to failure. We have a device that pushes down and it measures the newtons of force, and then when it breaks, it stops, it knows exactly what newton of force broke that denture. And so what we found when we looked down the load here, that the Ivo base with the individual tooth was about 247, and that's consistent with what we're finding in a conventionally processed denture across the board. The Ivotion monolithic was 324, and of course the Lucitone print I thought was going to be higher because I thought it was going to flex more, but it did not. Now the one thing I'll caveat with the Lucitone print material is we did not have it at 98.6, and with their advertised BAM technology within that bioactive material, there may be something to why this fractured lower because it wasn't warm. So the next level of our testing is now heating that material to body temperature to see what kind of result we can get. But Ivotion monolithic definitely stood out in the testing. So the work of fracture, when you look at, I get calls all the time on, what's the MPa of that base? Well, we don't measure denture-based materials in megapascals. That's a ceramic measurement. When we're talking about lithium disilicate or Empress or Zirconia, here we're looking at work of fracture. We're looking at newtons of force being applied. So a little bit of apples and oranges when it comes to comparing the materials. But here, with the work of fracture, the higher the number, and this also holds true when you're looking at ceramics, the higher the number, of course, the better you are. And a 26.39 or 26 is pretty high fracture resistance. And that's what it's taking it each time we run that cycle and we break that denture. This is giving us the statistic for the fracture resistance and or work of fracture. So the Lucitone with the individual bonded tooth was the weakest at this point. So then we took the samples and decided to break the teeth and see where those failed. Now we know with the process, the Ivo base high impact process is basically our standard. We have a lot of data on that. And that's 633 newtons of force to break that tooth. And those were all cohesive failures. You have cohesive and adhesive. Cohesive is the material broke, whether the tooth or the base, or the adhesive is it just didn't stick at all. The tooth popped out clean. 100% of the Lucitone IPN teeth popped out clean. Nothing held. In the lab we had make them, prides themselves on their quality, but it's just the nature of the beast with that photo resin and the polymerization. The Ivotion monolithic, again, those were 100% cohesive because there's no bonding interface there. So very strong. So our conclusions out of all the tests that we've gotten so far, the Ivotion monolithic denture has the highest load to failure. So when I talk about this denture being the good denture, I'm not diminishing the physical properties of the materials because they're very high quality premium materials. It's just you start looking at other things like aesthetics and indications you can use them on, and that's what then starts to diminish to a good denture, and then what you can do with it after that. So many of indications, of course, immediate and single arch dentures, upper and lower completes, the existing duplicate or reference denture is what I like to call them. This is not the copy denture. If you're familiar with the three-shape copy denture workflow, this is not that. You can't use that workflow to generate an Ivotian denture. They just don't work together. But if you call it reference denture and you start off in Ivotian, this way you can take and morph the teeth to pretty close to what the patient had originally. So you're kind of sort of copying the denture. You're just not using the same data. But I like the reference denture. That's the money maker. Impressions in an existing denture with some basic Sharpie markers. In this case, use composite resin in a Sharpie just so we could have a little bit of positive and a little bit more influence on it. And a bite. You need nothing else, and you can go straight to a final denture with this. Overdenture on 2 attachments all day long. It's kind of the standard of care anymore. Everybody wants locators, especially on the lower. If you want to do hater bars, sure. The other piece on the hater bar in the design, in 3-shape, there's some workarounds to get from one to the other, but you can definitely do the design and fabricate it. And then how do you bond the bar into place? Use the CAD bond PMMA material, or you can use multi-link abutment hybrid cement, something along those lines to help place that that housing. And then acrylic partials, the flippers. So the disc will work for a flipper. It's a pretty simple workflow. So in 3-shape, they brought in, like I last showed, the partial denture. So it's just how you set up the work order for the partial denture. In Ivotian, when you set up that work order, you set up the base, the tooth, and then you also have to bridge it, because this workflow is based on the milled tooth workflow, which has you bridge everything. But now we've got the ability, it doesn't have to be a full arch, we can select minimum of 2 teeth. If you got a 1-tooth flipper and you want to mill it out of this disc, it's kind of a waste, but you can do it, but you have to have 2 teeth on that work order bridged. And then when you get into the job, you can actually remove the tooth virtually and then move forward. But the work order is kind of demanding of wanting 2 teeth bridged. I call it the gingivator. I nicknamed it that when I got it as a beta test. The guys from Kyiv, now they're in Poland. Go figure. They got out like the day before the shit hit the fan there. But Tara sent me this to evaluate prior to the release of the beta, and I saw the gingiva, and I said, that's the gingivator, because that's like the terminator of all, so the gingivator worked, and it's kind of stuck. But these edge profile shapes is something to pay attention to. You have 3 different profile shapes that pop up, and it defaults to this one. And for my peripheral border, I'm not a fan of that. I prefer to move my slider all the way and get it completely rounded. I don't like that sharp edge, because what I've noticed with technicians when they're designing these dentures and they draw the border and then they get that sharp edge before it rolls back around, they always come in with the wax knife and they're smoothing it all off anyways and making it round. But the problem with taking the wax knife and using the smooth tool is it data averages. So it takes the low point and the high point and it brings them together. And at some point that low point is high, and that's going to be where it's rubbing the patient the wrong way. And so I really frown on using the wax knife to morph anything on the intaglio or the border. So I just keep that in mind. But I thought that was a pretty neat tool to have in there. The other one was the stippling tool. I struggle with that. I stipple all my dentures. I've done for years. I've done it. I just like it. I like the look. I like the way it breaks up the light. Also, as a ceramist, I like contour on my crowns. The way it moves the light around, especially on zirconia. But on dentures, when all you see is flat plastic, or not plastic, but PMMA, that's all you see. It looks like plastic because it's flat, it's shiny, it's hygienic, it cleans off easily, but boy, it just doesn't look natural. So a little bit of breaking up the light with stippling, and you can get as crazy as you want with it, but I really like that tool. And then the ID tag. This is one I like because you can, if your mill can mill the extra surface, this is nice because now you can come in with a negative and fill it with a colored cold cure, and you've identified, got the patient information in there. So I don't know how Texas is. Some states require having patient identification, nursing homes, things like that. They want it, so, my mom's denture is not ending up in the guy's mouth next to her, so it's, that stuff happens. But that's in there now, but again, the milling device, the camming software has to be able to pick up the extra surface to be able to mill it. If you're printing them, then they print great. So in the shell geometry, this is what it looks like when it comes in with the library you select in 3-shape. Now, as I go around and just show you a little bit here, the larger points will move the teeth and the geometry together. And then the smaller points move only the geometry, leaving the teeth in place. One of the keys to pay attention to, especially if you've got a closed vertical scenario, is that it does not penetrate. So you could see back there the little bit of penetration coming up through that blue shell geometry. That's going to cause a hiccup in the software as it's proceeding through. The software wants to design as it stops here, I wish I had a little sharper pointer. You can see the green line there where my finger's going. In the milled tooth workflow, the green line is where the software generates the gingiva. In the Ivotion workflow, it's generating the gingiva to the blue geometry. But because the software developers wrote the Ivotion workflow on top of the milled tooth workflow, the software is calculating both these interfaces. And if you've got pink showing through the model, showing through the geometry, it's now got a conflict. And if it's small enough, it's going to let you go forward, but it'll create an error in the cam output that the tool's going to try to get inside and mill a hole that's not there. If it's caught early on, the software will catch it, and you can just go in with a smooth tool and finish it off. So what I look for as I go forward with the design is I want to get that shell off the model. It can be right up close to touching. In any areas that may penetrate, that, like the little spot under that molar, I'll go forward, but when I calculate that bonding interface, I'm pulling the teeth out and I'm looking at the pink to see if I've got any artifact, any little spikes in there. If I do, I'm going to smooth them down. I'm going to take care of them right there. Same thing on the tooth. I'll look on the tooth surface, on the bonding surface, and if there's a little artifact, I'm going to smooth it down. So it's a little tip there that's going to keep you out of trouble and calling me going, why in the hell is my base not presenting? Or why do I got this big artifact flying off into the sky? It's usually that piece with the geometry penetrating the model. Don't pay attention to the stippling. This was early on in the development of it. I was getting a little crazy with it. The wax knife's a great tool. Like I said, on the outside, using it, you see the little areas that are penetrating the blue geometry. That's my basic virtual wax up. If you got any pink of your denture base coming above the geometry, it's going to be white. It's going to be tooth colored. And of course, underneath, if you take too much away and you see the necks of the teeth, that's going to be pink. So your geometry of your gingival trim is not going to look correct. So you really want it to propose to the geometry. Any little bit that has gone over, and typically where it has gone over is because of minimum thickness. If you set the minimum thickness, in this case I had it at 3 millimeters, And up near those teeth, I was pretty close to the model. It's going to present and protect that I have 3 millimeters. It also has a slide indicator for those familiar with 3-shape, that there's a little red, they'll show up red when they're falling within that, that minimum thickness. But it still presents the material there. It's not like it takes it away. You have to manually do that. So if I set it at 3 millimeters, I know I've got 2.5 to play with. I'll go ahead and just take that other 0.5 millimeter down to where I got a nice gingival trim. So in the implant indications, and you guys have been seeing these on the conventional side and the digital side, so we're really confident with this based on the science of the material and based on the existing dentures that we've done for years. It's the same material, just you're milling it. You can be very successful with these. So removable implants retained on locators, supported fixed with a bar, and then the supported fixed without the bar. And those are typically a more of a temporary type scenario where you're moving them in towards like a Zircad Prime restoration later. So how many are doing locators right now, conventionally? A few of you? Yeah, this again, like I said, is a no-brainer. Whether it's 2 or 4, you know, I think 4 is maybe an overkill sometimes, but especially, you know, on the lower, but 2 minimum. It's a pretty easy workflow in the design module. Do a little bit of blockout, you know, and then add a little bit to the top, because all you're doing is you're giving yourself a little more space for the pickup material. And then in the Smile Composer, you just go through, and again, make sure the positioning of the teeth are not impeding and overlapping into those junctions like we did with the base a couple slides back. Don't want to cross that green margin line. And then there's a tool in there that allows for this relief area. So I like to draw a nice even relief, even though I've already put some manual block out there. I like the option to have this nice even smooth relief added, and it maxes out at 0.35 millimeters. So it's not like you're adding a ton of space, but just enough. Then of course the drill compensation. So if you're printing, you know, the try-in or whatever, you know, there's no drill compensation, but when you're milling, you got to compensate for the tip of that tool that does all the cutting. You know, if it's 1 millimeter that's going in there and you got an area that's slightly under 1 millimeter, it needs to over mill to be able to get that. So that's what that drill compensation does. So you'll get a nice passive fit. You know, always check the geometry, make sure pink's where it should be, tooth is where it should be. Run the gingivator, do everything you want with that, and then and this may be the case where, you know, I may alter that peripheral border a little bit, especially when we get to the bar. You can provide access holes, you know, to do the pickup. You know, some people I know are preferring to do it direct without the access holes. But you know, you can always add it with the parametric shapes. 2.5 to 3 millimeter hole is big enough. You know, on that bar, that fixed supported, here's one where, you know, you might want that sharp edge to have a finish line too. So again, back on the indication, what you're working with is what border you'll select. So again, block out, you want to get rid of all that retentive undercuts and holes. This is, for those of you that have ever been to a Tom Wade conventional, this is that bar. That all-on-4 from Nobel. The same thing, go through, set your teeth. Again, keeping an eye on that green line, that if it starts to penetrate down where that bar is, you can morph the tooth and raise that green line up out of the way to give you a nice interface. And then again, the pink line is the relief, so I add that as well. In this one I would use the CAD bond, or even take it to the Ivotion, the Ivo-based injection system and inject right to the Ivotion base itself. And then again, providing the screw access holes. This is where it becomes a challenge, because the software currently does not allow you to put a hole through that bonding interface. even though it doesn't make sense because there is no bonding interface, but because of how the software is written, like I explained, so you got to stop just shy when you're placing these parametric shapes. So just shy of that bonding interface, and then in the base you do the same thing and stop just shy of it. And then once it's out, then you manually, gently grind the excess out. That's what it looks like on the tooth. You can see where they're partially stopped. And then come through and do the same thing in the base. Keep them slightly lower. You want to make sure you get them matched up as close as you can, so when you come back, you'll just have a thin area to cut out of there. The fixed implant without a bar. So temporary. This is that 8 month to a year scenario where you're going to transition this patient to a Zircad Prime full arch bridge. Definitely doable. Again, same steps. Block out, set the teeth, get the positioning of the teeth, the gingiva, everything done in the smile composer. None of that's changed. Keeping in mind that green line, that I got to keep that out of my design. No conflicts. And then again, relief around those temporary cylinders. And the one thing I recommend is if you have a clinician that's sending you the case from a iOS scan, that they scan these with the temp cylinders in place or the caps in place on the locator, not just send you the picture of the locator. It's the implant. That doesn't do you any good, because then you have to really design significantly open so you can fill it. Getting them designed with everything that it's going to be connected to is going to keep the bonding surface narrow, which is then going to give you options on what you're going to use, whether it's a resin multi-link abutment hybrid cement type thing, or it's going to be the CAD bond material or repair material, whatever the pickup material of choice is, in putting these together. It's always the thinner the better. You start getting too thick, now you can have some problems with the bonds. Again, here, this one's just applying some access holes to inject through, if you desire to do that. And that's kind of what it looks like. And of course, this becomes a whole nother can of worms, let's say, when you get to manufacturing, because now you've got all these holes or partial holes through, and we don't want to cause issues. So with that, coming out of 3-shape, when you set up the work order, you have a couple of options. You have the CAM5 output, which if you're in our program mills, it'll go direct there. It's going to give you the patient's name, the material, the tooth type, the insertion directions, the fissures. The only thing it's not going to give you is the stopping point for that burr to stop. It's going to continue to keep on driving through that hole until it gets to where it can't drive anymore and something's going to get broke. So there has to be a depth limitation. So that you would manually do right now. The depth limitation is not an automatic CAM5 function in the software, but it's coming in removable. It's automatic on crown and bridge, but in removable it's not. But that's the one piece that you'll have to do. Your CAM technician will have to set that depth limitation to keep that tool from going all the way through. And then, it just, again, back to lean manufacturing. The CAM technician is not sitting there fat fingering in all this data. It's automatically pushed, it automatically does the calculation, and you're good to go. When you come in with an STL, they're fat fingering in all this data. So it's a waste of time. So that's one of the benefits of the CAM5 system in the program mill. So here you see the red in the holes. That's where I want to put the depth limitation. Without it, it looks like that. With Ivotion, you have 3 strategies. You have in the PM7, you have a fast and a standard and a high. So depending on your choice of manufacturing, what you want that to look like afterwards. Here again, talking about depth limitations and setting those. That's really the only step the CAM technician has to do other than putting it in the disc, attaching holder bars, opening up the mill offsets, and sending it to the mill. So this is what it looks like. There is a depth step difference of 0.05 between the three. And that's what shaves off a little bit of time. So on the fast side, on both the intaglio and the outer surface, you're going to have a 0.15 millimeter groove around everything on both sides. It's slightly under milled. So okay, where would I use that? I think if I'm doing an immediate denture, you know, that the intaglio surface is going to be relined, you know, and ground on significantly, fast works for me. Or maybe fast is, yeah, my doctor doesn't like to pay me a lot of money, so I'm going to get it done, and he gets what he gets. So wherever you want to put it in your lab workflow. The standard, it gets a little better. Now we're at 1/10 of a millimeter of that groove all around. So a little easier to clean. You still got to spend a little time polishing the outer surface, but you know, it's a standard. It gets you down to about 2 hours of milling. And then the high is anywhere from 2 to 2.5 hours. And that's, again, there's not much. It's almost a smooth surface. When you see the dentures over there, you know, it's very little to finish, so it's pretty quick and efficient. I mill everything on high. I have my default set. I don't do anything less than that. I don't like to polish dentures. I used to have a guy for that. You know, that's just however you wish to set it in your workflow. But you have options. And this is in the PM7. In the PM5, 3, and dry, you don't have all three options. So you have a high and a standard. That's all because of you lose time when you're in those platforms because you don't have the 5 millimeter tool that you have in the 7. So the more robust spindle in that PM7 allows for a larger tool. So that hogs out a lot of material initially up front, shaves off some time, and the tools are also a little bit longer, and you get a little more in the 7, a little bit more of, because that longer tool, a little bit more access into undercuts. So you get a little bit more efficiency out of that PM7. So when I'm asked what mill to buy, because you know Ely and Trish will sell you any of the 4, but I tell them, you know, PM7 or you'll be disappointed. At some point. Can it mill a denture? Absolutely. But the PM7's the one, if you're doing zirconia, if you're doing PMMA, you know, you're doing wax, you cobalt chrome, you know, that one you're not going to be disappointed with. Where the others, you're going, oh man, I wish I would have bought that PM7. So when you look at the processing time, and I just threw the fast up here in this slide just to show you as a comparison. By the way, I had the question, what does MM stand for? MBA is obvious, you know, business administration, but the MM, some people don't know, is master's in management. So I have a dual master's. And one of my focuses in the MM is lean manufacturing concepts. So I'm also lean and Six Sigma certified. And so I start looking at this as a laboratory technician. This is stuff I wish I would have known years ago. And growing up as a technician in the Air Force, and Chris can attest, and many of you are prior military, you know, growing up we had a specific lifestyle in the military dental world. And we learned things, and a lot of what we learned was leadership, and really didn't get into process a lot. And it wasn't until my later years that the manufacturing process started to become more important, and these lean concepts started to evolve, and it makes sense. So I look at it from a numbers perspective here, in that single denture, you know, 90 minutes in the mill as a technician, I'm doing 90 minutes of work somewhere else. But look at the difference in the actual active time. The active time is hands-on. So from scan, design, to nesting, to the finishing, those 4 steps in the 5-step process of the Ivotion, I've got half the time in hands-on work with that denture. I'm off doing other things where I start losing time in say a conventional denture. So milling is very efficient. what's coming up next? You know, looking at, I mentioned expanding the tooth libraries to the Vivadent S anteriors. The Vivadent S PE DCL posteriors are the exact same posteriors that are in Phonaris 2. So the lingualized and the TYPs are the exact same form in molds that's in Phonaris. So there will be a very easy transition from a high premium tooth to the next step down is still a premium tooth into the third generation of double crosslink material, but with minimum anterior molds, because those are going to be the only anterior molds that are going to be available. And again, those are all based on existing sales data on what are the most popular. That's at the end of the day, that's what drives it, is the business aspect. You know, what sells the most, and that's where the developers take it. So this was interesting. You know, we're opening up the Ivotion base and dent into the Emac system. That's going to be announced. I think they announced it in Chicago, but how many were in Chicago? Yeah, no, I wasn't there either. So small show this year, but that was one of the announcements. So in the Ceramills, this is the one-to-one, the milled tooth workflow. And then in our ProgaPrint options. So we're going to have a try-in material. I've been playing with it. Finally got a shade nailed that I like. This is going to come out Q4. We may see it a little sooner as far as a try-in material. So that'll be really nice to have versus that butt ugly white disc that we have for the try-in material. The ProgaPrint cam, so those of you that have our printer, have seen our printer, or have ever worked with Cambridge, 3-shape Cambridge is a very, not my favorite camming software, but we've now developed our own ProgaPrint cam, so that will be out fourth quarter as well, along with the try-in material. And like I discussed about the denture base material, that one, you know, still keep it under your breath, top secret. I didn't say it here, but we're an innovative company. We're always looking at materials. And like I said, we're not going to introduce something that does not meet the ISO standard or exceed it. So I have faith in this one. So we have questions? Nothing? Man, I must have covered everything.
Is the Ivotion software, are y'all working on putting that in exocad as well?
Can't confirm or deny.
So yes.
The answer is yes. The short answer, long answer.
Maybe like within a year or so?
Yeah. Yeah, you'll see exocad and our scanner. We're introducing a scanner as well. Will come out, probably hit the market June or July.
So it'll allow you to design an exocad, but you still need to use one of your mills
For the Ivotion, yeah, monolithic, yeah. Yeah, that one, because it's tricky, because of the geometry of the disc, and being able to place it specifically in that mill in the right orientation, which for us, with our Cam 5, which takes the design over, and our disc holder keeps everything in alignment. So that's the difference. So I can only imagine that future, like just bringing Emac now to do the one-to-one milling and having the outputs to do these things, that at some point, you know, the competitors' mills will be included over time, but yeah, but for now, yeah, you got to be in a program mill to do that. The Ivotion monolithic denture is not planned in exocad until probably next year. Yeah, but the one-to-one should be.
What about the multi-material in the Ivotion discs? Is that coming soon instead of the? So right now the Ivotion disc just has the mono material, correct?
Right. Yep. The monolithic disc. Into the monolithic disc? No. No, it's really, when you take if you just look at the Ivotion dent, in the Ivotion dent multi, and you mill out the teeth and you look at them and you kind of go, I can see a little bit of difference. the way we've designed the material to be a little more translucent in the thinner areas. So you kind of get a polychromatic look anyways. So this multi-disc in sales of the regular dent disc are up here. You know, so even the base disc, you know, when I look at just the base disc, its sales are down here. So that's telling me people are buying the dent, milling it, and putting it in a printed base, you know, or somebody else's pink base. But right now that's kind of the gold standard for the tooth out there. In the look of it, in your hand, yeah, you can probably see a little difference. Hold it up to the light, but when you get in the mouth and conversational distance, you can't tell the difference. So if it was Bill's lab in the basement, I'd probably lean a little bit more towards the dent. Now, probably some of the future developments we'll see is the double crosslink material versus just the highly crosslink. So stepping it up, but when you do that, it starts to add cost. Right now, that disc, and I started saying it's a economical disc. I didn't tell you how much. It's $105, I think. I don't know, Ely, where'd they go? See, they're not even listening to me anymore. Don't shake your head, because it depends on how much money you spend with us, what kind of discount you get. You guys know the game. But yeah, but so like $105. So if we go to a double crosslink material and we improve it, well, guess what? That's going to make it a $125 disc. So it's starting to, you know, diminish that effect that we wanted to compete with the low-cost printed materials. So that's kind of the marketing scheme. For a dental lab tech, I'm pretty smart when it comes to that, because I sit in the meetings. It's kind of nice to be in the know about it, and I'll never lie to you. So that's something, you know, I may skirt a question, but yeah, but it's one of the things, because I'm the guy, like Ely said, I take the phone call. You know, when, you know, my team is, you know, I think we're the best on the planet at it, and when the phone rings, or I get an email on a Saturday from some obscure lab in Michigan, you know, they got design problems, I answer it. That's just how we roll. All right, let's get into Prime, and then anything else, I'll be at the booth the rest of the afternoon, so I'll still have a voice, I think, because I didn't drink last night too much, so saving it for tonight. So Zircad Prime and Prime Esthetic, how many are using Prime? Number of you liking it? Yeah? Yeah, maybe I'll get you to like it a little bit more as we go through this. So I'm going to cover real quick the Emac system, because I have to cover the system. A lot of confusion out there. Some of the physical properties of zirconia and how to choose the right material. The dominant impact of the multi-layer zirconias and what it's had in the market recently, and then some elements for success or some tips and tricks. So when you hear Emacs, the first thing that always pops to mind is lithium disilicate, is Emacs Press, Emacs CAD. That's kind of that was the moneymaker of it, but it's a family. You have obviously the press lithium disilicate ingots, you got the blocks, you got the nanoflora apatite glass, you know, the layering ceramic. That's also Emacs. It's not lithium disilicate. The fluoroapatite glass and the Zirpress material, and you got all the Zircad materials. They all have the Emacs brand name. So when the dentist asks you for Emacs, you really got to ask, what do you want? If you want lithium disilicate, then I know what I'm doing. I'm pressing you a crown, or I'm milling you a crown out of CAD. But if you want Emacs Prime, well, sometimes it's also an education part for you back to the doctor going, well, Prime's their new lithium disilicate. Well, you go, no, it's not. Emacs is a family. This is where it falls in the family. So the dentists have a short attention span when it comes to the material science piece. So sometimes we as technicians have to re-educate them. So all the Zircad materials, all the way from the medium opacity all the way up to the latest Prime Esthetic, are available. So we know that when we look at zirconia and the physical properties, you know, it's the high strength that's drawn us to it. When Chris and I started using zirconia back at Sembach Air Force Base in Germany, when we went through the first training of it, we were told it's the white metal. How many heard that before? It's the white metal. So what we treat it like, as a ceramist, I treated it like metal. You know, I did everything wrong to it, and I didn't really understand the material. But the more I got to understand the material, changed the way I handle things. So we know when zirconia is heated, it changes the crystalline structure. It goes from the monoclinic to tetragonal to the cubic phase. So based on the temperature and the time, and I think, who was it? Was the guy before me, the Argent guy? Was that the one that went over material science? So, I mean, and that's what his gig is. I mean, he's a material scientist, so he's got this down. And, I didn't get to see his presentation, but I know he probably drove it to you. So I'm just going to hit the high points of it from understanding it from a technician perspective and how we apply it. The various stages of yttria, again, provide that strength or translucency. And when we look at the 3 Ys, those were the original ones. Like I said, Chris and I started working with. They were the coping materials. And so we got to know those pretty well. A lot of tetragonal, about 100% tetragonal phase in that. No cubic, so no transitional phase. And we talk about transformation toughening. Did he talk about that at all in zirconia? Nobody took notes? Okay. So I'll be safe to talk about transition toughening real quick. But there's a volumetric expansion difference between the monoclinic and tetragonal. And what happens when you look at this frontal zone, the frontal zone with all that tetragonal crystalline structure here, the energy, what you need to shift to the monoclinic crystalline structure is energy. Whether it's heat energy, it's force energy, the crack generates energy. And so the more of the tetragonal crystalline you have there, then that energy gets slowed down. Where when you're in the monoclinic, it tends to be weaker. So you'll see it's like a wake. So the wave coming in will diminish as it hits the shore. And it's kind of what it's doing when it's hitting all that tetragonal state. It's slowing it down. And so the cracks tend to heal themselves. Now when you go, this is important, when you go to, say, a 5Y, a high translucent material, and you treat it poorly, like sandblasting the crap out of it or grinding hot and heavy on a occlusal anatomy, you're generating that wave. And it begins that crack force. It may slow down at some point, but then when it gets to the patient's mouth, there's another force being applied which pushes the wave again, and then eventually it cracks and it's weaker. So there's certain things that we as technicians do to zirconia that we need to minimize this wave. So the 3 big ones that are out there, the 3Y, again, 100% tetragonal phase, the 4Ys, a little more translucency, about a 75% tetragonal phase, in the 5Ys, or the higher translucency, about a 50-50 mix. So obviously with that comes degradation in strength. You get more translucency, but you lose strength. And you also lose its ability of that fracture resistance, kind of like I talked about with Ivotion, that fracture toughness. So as you move down, it becomes easier to break. So framework materials, the A is for ABC, so one of the first ones out there. Flexural strength pretty high, typically around 1,200 megapascals in flexural strength. We know that's pretty consistent across the market. Again, frameworks, we layer them to make them aesthetic. Proven material, proven technology, time consuming, labor intensive, yes. But you can turn out some very beautiful restorations. The monolithic option, though, when you're in the 3Ys, you definitely don't want the monolithic, in an aesthetic zone in the 3Ys. But this was the evolution of monolithic ceramics. It wasn't necessarily CAD. It was pressed before CAD, but Empress, and then lithium disilicate came along, and then zirconia came along. And so the LT materials, 3Y materials, relatively strong, but kind of butt ugly as themselves, you know, in a monolithic state. So you had to you do a little micro layering. So the same materials we're used to, just with a little different shading. And then the demand for more translucent materials came out. So it was, the MTs started to show up. So our Zircad MT, the SageMax Nexier Plus, you know, these were nice materials. You know, again, you know, we start incorporating more cubic phase for that translucency. So we start losing a little bit of strength. They're about 850 megapascal in flexural strength. And that's kind of what the grain structure looks like. The strength over the HT is about 850, like I said, 6 to 650 for the 5Y materials. Limited to 3-unit bridges. We're in pretty much the Emac press or CAD indication range as far as single units and bridges go, except you can incorporate a molar as a pontic or a molar as the abutment here. Preparations are a little bit more critical in that you're looking more towards that all ceramic deep chamfer or shoulder. You want to have you would definitely want to have support. In the 3Y materials, you can get away with more of a feathered knife edge margin and finished off to, again, depending what type of cement they're using. But when you start moving into the 4Ys and 5Ys, now because of that fracture toughness is diminishing, you also got to pay attention to margin strength as well. So some of the HTs that are on the market, again, these are around the 650 megapascal in flexural strength range. And again, about a 50-50 mix in the cubic phase. So where would we use them? Again, 3-unit bridges, similar indications as Emacs, press or CAD. They got good aesthetics. Don't need layering. You can layer them if you want. Micro layering, typically, you know, in the anterior, posteriors, you know, you leave them monolithic, and you can do some nice staining and glazing and dial them in. Clinician's report came out and identified, you know, there is an increased rate of fracture with these 5Ys that are out there, and so just the caution is, you know, pay attention when the doc is asking for these or you're giving them this material, that the preparation supports it. A lot of these fractures are because of that and mishandling. So going below minimum thickness requirements and cutting embrasures into bridges, things like that. You know, so when you're thinking about how you're selecting what material you're going to use, you know, obviously they all can be used for molar replacements, you know, single molars, you know, paying attention to, you know, the prep thickness and things like that. But, you know, it's really the T's are the ones that are indicated for the longer span bridges. So you don't want to go out there on a 6-unit bridge and try to put a MT material or a 4Y or 5Y in there. So you want to pay close attention to the indication and the material selection. So the latest developments, of course, is the multi-layers. So these are multi-layered, and I threw Katana in here, just was what I had on my bench to compare it to. The single-layered, multi-layered single powder. So 1, 3, or 5Y material, and there's even some of them call it a 6Y. There's no category for a 6Y yet, but there's just more closer to that. There's some of those that are out there. Again, keep in mind it's a weaker material, but it's all the same powder with different degrees of colorants added to them. And so there's not necessarily a different degree of translucency or cubic phase. It's all the same powder, just shaded differently to provide that polychromatic look. And that's okay. You know, we've had to start somewhere, and it's kind of what this looks like as it goes through. So varying degrees of chroma coming up through, and that's what's going to provide you that polychromatic look. So we know the three that they have out there right now. And there's plenty of other manufacturers that do the same thing. The multi-layer, multi-powdered Prime is the only one on the market. There's nobody else that has a 4Y to a 5Y and a 3Y to a 5Y with the gradient technology. That's patented. We own that process, and that is the only one on the market with the gradient technology. The other ones, the 4Ys in the SageMax, in the MT Multi, those again are two different powders. They're a 4 and a 5Y material. Of course, as we know as ceramists, when we're working with different materials, there's coefficient of thermal expansion differences. There's all these things that are going on. And of course, with a 4Y and a 5Y or a 3Y and a 5Y, there's tremendous amount of things going on between those two if we just stack them on top of themselves. So as they sinter and they go through that dynamic, the sintering kinetic for each of those materials are different. So they cause stresses among themselves microscopically, but what you end up seeing is, bridges rocking, perhaps cracks or delamination between the materials. You can see lines. Things like that happen in those materials. So we did this gradient technology to help overcome that. This one is just showing you what the Zircad Multi and the Nexeer Plus look like. So really what we've done here is the layers with the 3 zone of the gradient strategy, or not gradient, but gradation, because 2 different things I'm going to talk about there. So we try to get a nice even transition zone. When you look at the difference in thickness, this is one of the things technicians call about a lot, is it doesn't meet the shade. It's not an A2. I mill it out of an A2, it's not an A2. Well, they're at 1 millimeter in thickness for that anterior crown, or they're at 2 millimeters in thickness. It's too much chrome. It looks orange-brown. So some of these, it's all driven by color or in thickness. So you may hit an A2 slightly lighter. You may have to stain it a little if you're on the thinner side, because you don't have the mass to drive the chroma through that. So thickness is an important one. The MT Multi is very nice material. It's been flying off the shelves. It stains, it glazes beautifully, easy to match. But then the development of Prime. So the 1 disc, 1 solution, until the Prime Esthetic came along. Now we have 2 discs to cover all the solutions. So, like I said, completely different than any other zirconia on the market with that gradient technology. Starts off with the same 3Y and 5Y or 4Y and 5Y material, but with that gradient science we have in there, that makes a difference. It brings that sintering kinetic much closer together, so we get some excellent results. With the Prime Esthetic, get my clicker to work. With the Prime Esthetic, they wanted to maximize the aesthetics with the combination of these 2 powders, because we already knew the MT materials were looking really nice, but now we wanted the more precision with the gradient blend and the fits to be better. And so with this gradient technology, you'll see no seams at all. So as we look at this, they just line up nice and clean and transition. So there's a lot to think about when you're using this disc. What happens, and I mentioned the sintering kinetics happen at different times. The 3Y materials, and this is Prime, for example, the 3Y material in the tetragonal is sintering quicker, right? And then on the cubic side, on the 5Y material, we need that cubic phase, so it takes a little longer to get there because we've got to stay at the heat longer. So the sintering kinetics are different. And what happens with the transition layer in between, if these don't match up, you start getting lifting, pulling, tearing, cracking, and seeing lines. So what we've done is, and this is the piece that is patented, is the inhibitor and the activators that are placed in the chemistry of the disc that help push the cubic face to go quicker and the tetragonal face to stay longer and have them center at the same time to keep a nice even homogeneous centering. So what you see on the left is a slice that was not with the gradient. So you can see you start to get a little bit of a warpage. You know, the black line at the bottom one, it shows it's pretty relevant. Up at the top is, to the left side of that is the translucent portion, and it's being pulled away because it's taking longer to center, so it's kind of slumping off there a little bit. Where on the right side of the slide is with the gradient technology, and so we can get a nice homogeneous centering kinetic between the two, so we don't have those stresses. So pretty much guarantee perfect fits every time. So when you're on an implant scenario, you know that you want that to fit precisely. So this is what the disc looks like in regards to the position of the material. In the MT material, it's a 20% section in the incisal and a 20% in the gradient or the transition, and then the rest of the disc. And that's across all sizes of the disc. With Prime and Prime Esthetic, you have a 3 millimeter of the 5Y material, you have a 4 millimeter of the gradient technology, and then the rest of the disc is made up of the 3Y or the 4Y if you're in the Prime Esthetic. So the disc concept's the same all the way through, so you're not guessing or having to do the math of the 20% to balance off your translucency. So right now there's a 14 and a 16 millimeter disc in the Prime Esthetic and a 16, 20, and 25 in the Prime. The Prime, we have universal, because you can, if you're back to doing a coping, you're covering a dark stump, you know, you put it down in the 3Y material, you put your coping down there, while in the mill you still have a monolithic molar or central or micro cutback central, all in the same disc. You don't have to jockey 2 or 3 discs to get it, you know, so you've got one disc that does it all in that regard. We won't see, I don't want to deal in absolutes, but on the 16 millimeter disc, I don't think we're going to see a 20. We may be, yeah, but I think the target for that is, you know, is not there yet, because we know we put a 20 millimeter disc, you all are going to start milling full arch bridges out of Prime Esthetic. So we want you to do those in Prime. That's your safest bet there, because it's the stronger material. So the one disc, one solution, obviously you have plenty of options with this disc. And those that have used it can probably attest, you figured out the positioning and the size disc that you want to use for your production. I recommend staying a little larger, around the 20 range. You know, you start getting smaller, it starts to limit what you're going to be able to put in that disc and where to place it. So all indications for the workflow. You know, infiltration technique, absolutely. A little added infiltration liquid for some special effects. Staining technique, micro cutback, you know, layering with the power incisals or just the regular incisal material, or even a full layering technique. It gives you plenty of options. And of course all the indications, you know, all the way up to a full arch bridge with no more than 2 ponics in the span, so that's just something to keep in mind. I know I see a lot of the implant bridges that may have 4 anterior ponics, but then you also have a huge mass of gingiva underneath it. So I think as long as you've got the larger connector source there, it's going to be strong. You know, you're not going to risk cracking. That's barring anything, you know, that you do negatively to it. But I think the thicker the restoration, you know, the more success you're going to have in that regard. So with the Prime Esthetic, you know, you're looking at a very similar translucency to the lithium disilicate in that range. So in the medium translucencies. So 1.5 millimeters is where we target our shading. And so everything that we do, when we tell you what shade to select, whether it's an ingot, a block, a disc, it's all targeted around 1.5 millimeters. That's our shade standard. So keeping that in mind, you know, you're going to be a little thinner, it's going to be a little lighter in chroma, you're going to be thicker, you may have a little bit more intensive chroma. So suitable for cutback, not necessarily needed with this. I mean, pretty accurate shading. We're one of the few zirconia manufacturers that shade our own. And so all this is done either in New Jersey, at Somerset, New Jersey at our manufacturing plant, or in Shawn, Liechtenstein. But they're all done batch specific and shaded by us. We don't buy the powders pre-shaded for the Prime Esthetic. So we want to ensure that this is dead on the shade standard. So some key elements or tips or tricks here. You know, the characteristics of the two I covered, and the strength, keeping those in mind. You know, the perfect shade match with the Prime Esthetic. Single units, 3-unit bridge, ideally monolithic, maybe a little micro layer, but really not necessary. Where you need the more strength, when you move over to the Prime, you're going to get a basic color match. You're going to be pretty close. It tends to run a little higher in value. It tends to be a little brighter than normal zirconia is in that range. But that's good. I'd rather be a little brighter than darker. You know, and then I can always shade it up. So brightness is important. The dentin translucency, obviously it's going to be less because it's that 3Y, that's that T material, so it's going to be more opaque down there. So it's going to give you a nice gradient, again, depending on thickness as well. So where do you use it? You know, like I said, single crowns to full arch bridges, micro layering, full contour layering, and then, you know, ideal for micro layering. I think I have a picture coming up of one of the bridges I did. Discolored stumps, of course, you would use the Prime for that because of a little bit more opaqueness to hide a stump. The traditional wall thicknesses with the aesthetic, you got to keep that in mind. You can use minimal wall thicknesses with the Prime just because of its ability to block a little more. With the Prime Esthetic, and if you do micro layer it, I'd recommend you use the power incisal, so that it's going to help it from dropping in value. That's why Prime is a little higher value. The material scientists chose to keep it a little brighter because we know that the more translucent materials that are out there, when they go in the mouth, they become dark suckers. So they tend to go gray. And so Prime will help combat that, where Prime Esthetic, if you cut back and you start adding more translucent material on it, it may give you a little gray look in the mouth. So the power incisals are designed to keep that vitality. So it's a very good ceramic powder to use when you're micro layering, especially on high translucency materials. Just keep that vitality going. So really, just glaze these, you know, stain and glaze. You can make them as pretty as you want. Micro layering and glazing techniques option there. I think I've beat that dead horse. So in the process in the lab, you know, from milling the restoration to the final stain and glaze and out the door, there's a lot of things that happen, as you guys know, you know, that can really affect the final outcome. So if we go through and we look at a few processing steps and what's affecting the color, the translucency, the brightness I've talked about, you know, we can count in our heads how many steps we're taking to get here. What do you think about polishing? You know, a lot of clinicians, I know chairside clinicians are polishing zirconia right out of the mill. You're not staining and glazing at all. Are there any clinicians in here? I'm hoping we're all lab techs, going to talk bad about them. You know, if we sent them a crown that looked like that, you know, what would we get? You get the nasty phone call back going, what the hell are you giving me? Yeah, and they're not going to pay you for it, but it's okay for them to do it. So the different, I've seen that a lot. That's about as bad as I'll talk about some of the dentists out there. But polishing is a quick and easy way to get there. Of course, staining and glazing, it will give you a little bit higher aesthetic. The minimum steps when you're polishing is 5. You do the design, well, not counting the scan and the prep and all that, but going to the nesting, the processing, the sintering, and then just polishing, where you throw a few more steps on with the stain and glaze. But I think you get a much better result. Not a bad polished crown. That didn't take me long to do, to get a little spit polish and get it up there on a slide that's, 6 foot high, it looks okay. It would look okay in the mouth. I probably wouldn't do it for an anterior, but maybe a posterior would be acceptable. But now you got something more complex. So now you need to get a little bit of staining in there. You need some mamelon effect. You need some characteristic to that patient specific, especially if you're trying to match 8 to 9 or 8 and 9 to 9 and 10, 10 and 11, and you got all the different scenarios you guys deal with every day. It's like, how do you get there? And it really, you can get there staining and glazing. In this, I used Ivocolor on this. There's a couple extra steps to get there, but I think the final outcome is much better. Like I said, perfect match to shade because we shade all these powders ourselves. So very close, almost exact match. And again, depending on where it's nested in the disc will also drive the translucency. So those are all the ones with the highest risk, really. These are the ones where we can mess up as a technician. Let's talk about nesting. I get a lot of calls, and the digital team gets a lot of calls on the nesting and how to get the best effect for the nesting, keeping the disc parameters in mind when we look at these. The higher we go, the more translucent it's going to be and less chroma when it's in the material. And this is a good example. So it's a little brighter when it's nested higher. When it's nested lower, it's a little more chromatic. Then we kind of come in the middle there, and we kind of get a nice little blend of translucency. In our software, this is the visual you would see within the nesting software. And so you'll see, because it came out of the design, knowing you're going into Prime or Prime Esthetic, it's going to give you the positioning of those layers in the disc. And so now you can adjust the crown up and down in the CAM software. So the picture on the right is showing, a minimal sized disc. Maybe that's a 14 millimeter disc, and that's about all that disc can hold that crown. We take that same crown and we move it over to a 16 millimeter disc. We got a little wiggle room, so now we can move it up and down and get it into more of an ideal transition. And to me, ideal is about 1.5 millimeters on anteriors from the top of the disc. Remembering that top 3 millimeters is your translucent material. And so the higher you go, the more translucent it's going to be, but you're also going to lose shading, that chroma. So we want to, be about 1.5. Yeah, add 5 to that. Yeah, the molars, because they don't tend to be as translucent in the cusp tips, so and a lot of times you don't have nice cusp tips like this, so a little lower in the gradient. So about 2 to 2.5 on a molar. Definitely affects the brightness. So you see Prime and Prime Esthetic, and you see the chroma in the Prime Esthetic. Because we get the more translucency, we get the prep shade coming through, everything dials in nicely. Where in the Prime, we're a little higher value, so we're close to the shade. So if we're calling this an A2, I'm close to an A2 in Prime. I'm nailing it on Prime Esthetic, but I'm going to have to stain a little in Prime to get it there. So just because of the nature of the beast of that 3Y material is what's driving the color here. And again, the developers kept it a little higher value to help combat that grain effect. So, shade guide match, I'd say so, pretty close, and it just has a little bit of glaze on it. do everything with prep dies, natural dies, stump dies, whatever you want to call them. You got to get something underneath there because these are still translucent. Still drives the shade, so always put a stump die in there. Again, just showing the effect again being too high. It kind of drives off the color, but translucency, but still acceptable. A little bit of stain and glaze will get you there. And then the sagittal dimension. When we're working in a 20% rest of the disc, we've learned to rotate on the sagittal to get a kind of a gradient transition going through. Don't have to do that with Prime and Prime Esthetic because of our gradient technology. You definitely don't want a labial because the labial will shorten that transition zone. Straight up and down is good, and a little bit to the palate is even better in that regard. And again, it gives it a much more harder and prominent transition. This starts to blend it, and again in the software you can see where it's positioned. Neutral position works best for most patients and most shade tabs. Maybe you don't need so much in the posterior, but need a little bit more in the anterior, or just to get that bridge to fit in the disc. Maybe all you have is a 20 millimeter, you don't have a 25 millimeter disc, and you got to squeeze it in, and maybe that angulation is the best path for you. A little bit more palatal is better, never to the labial. So pre-sintering process, this is where we get into some challenges. We all clean them off pretty good. For the most part, we'll blow them off or brush the mill particles off. Some people use that ProArt polishing wheel, which can provide contamination, and there's also modeling that occurs to the moly heating elements and the condition of the sintering oven muffle. There's things that happen during the cycle. So pay attention to what you're using to grind on these materials. I recommend never using that ProArt wheel. Those were designed for polishing acrylic and soft reliners. They really weren't designed to shape or contour or smooth zirconia, and what they do is they leave material impregnated on the surface. So be careful with those. This is what happens. The picture in the middle is of the wheel rubbing on the surface. That's embedded. And when I get the phone calls that, nope, it's the disc. These white spots are inside the disc. Well, I know they are, but they started on the outside. The one on the left is residue left over from milling, so grinding residue dust I didn't get off. That easily sandblast off. Now when there's something that's further in white, that's not because the disc wasn't properly mixed. That was because something fell on it or something was left on the surface. So remember, we're starting at about 25% larger. And as this is going through the sintering process and organics are burning out, when the material's coming in, what happens is that speck of whatever, it could be aluminum oxide because the last thing you did was sandblasted something. You had got hairy arms like me, falls off on the bench and you pick it up and you have it on your hand and it's on the crown. That little speck of aluminum oxide gets pulled in the surface. And what it does is it acts as a separator to the crystal structures forming. So and basically it just kind of works its way down and you'll see the disruption from around where that is. The one on the right is the modeling coming out off a old heating element was shedding the oxide. So when you look up and you see the heating elements and they got the little scaling, run the cleaning firing, get rid of that stuff and clean the furnace out nicely. But that all settles on the surface and falls in during sintering. That's kind of what it looks like. SEM shot up close there in the top. This is one I did. One of the first complaints came in, and I did some testing with the materials. The analysis on the left was the spots I found on the crowns, and the analysis on the right are of those We don't put tungsten or boron or carbon or silicon all in at, this. Silicon, yes, there's a little bit, but not to this level. Alumina, there's alumina in there, but not to the level we're seeing. In this lab was, a soup sandwich, I like to call it. They had a guy that was sick, had another guy that was doing all their divesting of their crown and bridge work, doing the finishing of zirconia, and so he had, when they sent me a picture of his workstation, everything he was doing was just contributing to the previous slides. So all those white spots. Let's get into sintering real quick. I know it's getting close to lunch. I want to leave it open for some questions. Programmat S2 is our new generation sintering oven. We have 3 prime programs in there already dedicated. There's the speed, single unit crowns, the 4-hour speeds for a 3-unit bridge, and then of course the standard 9-hour, almost 10-hour program is going to cover all your needs. So very good results when you compare them across the board. From there, I can't tell if it's a little washed out or not. On my screen, they look a little better. But you see a hint of a little more chroma in the shorter cycles. There's just a hint of chroma if you look down at the cervical, compared to the other. So that's why I have the slide on the right, the picture of the 2-hour 25 and the 950. That's showing the kind of the dramatic difference. You see a little bit more chroma in the 225. So if you're a little behind the power curve on the heating, you load up the tray, you've got massive thicknesses, implants, that kind of stuff, you're going to end up with a little more chroma. If you're in a competitor furnace, you may have some other considerations. Let's see if I can wrap this up. So follow the recommended parameters. Third-party furnaces, you guys have them, you're using them. Some of them you've had for 17 years. Just pay attention to their use. Things I look at is the accuracy of the muffle. Can they be calibrated? Are they limited on temperature? Some go to 1500, others go much higher. Again, do they stack trays? Do they use sintering beads? All that kind of stuff really affects the final outcome. So I've tested all those furnaces, and these are what we came up with as a recommendation firing parameters for both a speed cycle and a long cycle in all competitor furnaces. Again, it's a starting point. And we also give you a little guide to show what to look for. If you're seeing a little orange-brown, you're under firing. Need a little more temperature, bump the temperature. You're seeing a little bit more washed out, a little more translucent effect. You're firing too high or too long. You got to bring that temperature down a little bit. So competitor furnaces, you kind of juggle a little bit. As ceramists, we do that generally with our porcelain ovens, so to get our final firing effect. Crackage and breakage. I'm getting there, John. Cracking and breakage. Of course, you get bridges like this that come in and they're cracked. Obviously, not enough sintering supports. But the support they do have is a huge mass. But what I found is a lot of times they've cut into the interproximal with a separating disc. And when they've done this, that's where the crack begins. Again, going back to that wave action, you start that point there, and that stress will continue to push through. And this case broke in the mouth. This is a different patient. They placed the connector too high up in the 3Y in the gradient zone, and so the strength is down lower, and it has a the ponic is just kind of hanging out there. So, that cantilever bridge, just didn't have much prep to hold on to, and it broke. So we give some good guidance on supporting it. These are done in a competitor CAM software just to show you what to look for. Make sure, get over there, come on. Make sure everything is perpendicular on this large bridge. If you want to fill this in, make sure you have supports going perpendicular straight up and down here. Same in the posterior. You want them all to be up and down, and that's just going to help you because of gravity also takes effect when you're sintering. And these are our recommendations for in our furnaces. We can cut the holes out of the mass support. And single units, the one I have on the right is a large implant bridge. It is a lot of mass, so I did every other unit. The top one on the left is just a bridge without gingiva. You want to go every unit on the internal aspect, and that's going to provide the proper support and stability for the sintering. We talked about glazing and polishing, what things look for, some of the materials I use. We can talk about these later. Our optogloss materials on our clinical side. You may have experienced this, polishing, pre-polishing before glaze. You can superheat the surface and that will shift the color of the surface. So be careful on any pre-polishing and how fast you go and what rubber or silicone wheels you use. Fluorescence, we'll talk a little bit about fluorescence just in that you understand these do not fluoresce. You have to use a fluorescent material to glaze them, such as Ivocolor, fluoro. Layering and infiltration liquids. The infiltration liquids, the key I want to put here is we do have a combination to 3D master. So you can go A to D, from A to D shade to a 3D master with just some simple one brush stroke technique with the LT infiltration liquid, and I have that guide available. So natural dye, stain and glaze. I won't get into Ivocolor. I threw this in case I was talking way too fast, which was not the case. Layering and firing. I've been in labs where they load the furnace up, they load the tray up. Just keep things nice and homogeneous. Heating elements around to the outside. You keep things to the outside, closer to the heating elements. They tend to come out a little bit better when you're glazing. And that should wrap it up. Lunch. Thank you. Yeah, no, I can talk over it. Appreciate your patience. If you got any questions, I'll be at the booth after I eat. Thanks.